Now we will learn about Rödl Nibble. And the reason why we call it Nibble, I will explain about that later. But let's just define some things. And we have defined the hypergraph before. And now we will learn about matching in a hypergraph. A matching in a hypergraph. Say is a collection of vertex disjoint hyperedges. So again, graph is two uniform hypergraph, and there if you say a matching, that's disjoint edges not sharing any vertices. For a larger uniformity, you have this triangle. This edges, hyperedges. These hyperedge and these hyperedge, if you take them, then they don't intersect at any vertices. So they form matching. So that's what we call matching. And for a given hypergraph, H, and say S is a vertex set, we write the degree of this vertex set S be the number of HE inside of H, which contains this S. So vertex degree is the number of edges containing this vertex. That's how we define in the graph case. For hypergraph case, the edge might have a size bigger than 2. So even if you have 2 vertices UV, you consider all the hyperedge containing those 2 vertices. You can also consider that. So for any collection of set, we can actually define this degree. And we can also define the maximum degree or minimum degree in a more different, several different way. So you consider all the sets of size I, and then you consider the maximum degree among all sets of size I. Then we say that this is I's maximum degree. And maximum degree of H is the maximum vertex degree. And we say that delta 2 is we call maximum co-degree. So we consider all the pairs of the vertices and then consider the degree, and we choose the maximum one. Then you will write delta 2. So what do we do? What we want to prove is this theorem by Pippenger. So for given epsilon and k, there exists delta 0 such that the following holds for all 1 over t and delta both smaller than delta 0. So epsilon and k are given, and there exists some delta 0 which is bigger than 0, such that the following holds for as long as delta is smaller than delta 0 and 1 over d is smaller than delta 0. So it means this capital D is large. And what happens is that if H is a n vertex K uniform hypergraph satisfying the following. So one is it is almost regular, meaning that all vertices of H has degree 1 plus minus delta D, and it has a small co-degree. That the maximum co-degree is smaller than delta times D. Then H contains a matching of size at least 1 minus epsilon times n over k. So there are n vertices, and each H has size k. So if we have a perfect matching covering as much as possible, then the size is n over k, or depending on the whether k divides n or not, but more or less n over k. What this says is that the epsilon is arbitrary thing which we chosen. That's right. We're given epsilon positive and k integer. So we want to find the almost perfect matching as long as the graph, this hypergraph has almost regular condition that all vertices has a degree more or less d. So this delta is small, so that means its degree is very close to this d. And small co-degree is that every pair has not many edges actually containing it. Actually, let's write it this way. Possibly, except delta n vertices. So it doesn't have to be that all the vertices have the same degree. Okay, let's not write this now. For now, maybe later we can actually adjust this, but let's write it this way. And we can actually make some exceptions of a small number of vertices. But for those vertices, we also have to ensure that it has not too much degree. So the statement gets a bit more complicated. So let's write it this way. So this essentially says that if you have a hypergraph which is almost regular, and then its co-degree is small, then we can find the almost perfect matching. And here we will actually write this in a different way. So if we write that say A is much smaller than B, less B, then it could mean several things. In number theory, it actually means that A is big O of B. And in combinatorics, we have one of the two things. So it's either small O of B or the other usage that I'm gonna explain. So lots of papers actually use this notation in different meaning. So these two are clear. So sometimes you write this, sometimes you write this. This is, as far as I understand, lots of number theory people or some computer science write it this way. In combinatorics, most of the time I think they write either this or this. So the other usage is the following. And sometimes we write that in this way. So if 0 and 1 over d delta epsilon 1 over k 1, then the following holds. So the other usage then I'm going to explain is that this, instead of this, what we can show what you can write is the above statement is that if you write it this way, wait, I'm just writing the same thing twice. Okay, let me just explain. So when we write a statement holds if, say, x is smaller than less and less than yg1, if we write it this means this for given yg there exists x0 which is determined by y and g such that the following holds if x is smaller than x0. So if you write it this way, that it means that for given yg there exists some threshold, and then as long as x is smaller than statement holds. So in other words, it means that there exists some function, say x0 or f, such that the statement holds as long as x is smaller than f of yg. So this statement can be fixed as then for given epsilon and k, we bound these two smaller ones. So we can say that suppose this, we can write it this way. So you can actually notice that this existence, is from right to left. So one of the downside of this kind of notation is that sometimes we need the number to be large, sometimes we need the number to be small enough or large enough to make sure that the statement holds. But if you write it like some big number, small number, big number and small number, then it's not clear where you start. So it actually means we fix something, and then for that we have another. So we have to start this statement from somewhere. So it's not really clear if you write it in this way, where something is bigger and something is smaller. So we we have to decide where to start. So usually what we do is we start from 1. So from right to left. So that you write the big numbers, you convert into small number by writing 1 over big number. And one of the merit of this notation is that you can actually simplify the statement a lot. There are some statements that we need to prove, something like this. So let's say x is smaller than yg, w u p k 1. Let's say in that situation, if you formally write it, for given b k, p and 1 over k, say, there exists, say, alpha 0 such that the following holds. And for given WU smaller than alpha 0 and 0, there exists beta 0 such that the following holds. And for again given YG, which is smaller than this beta 0, there exists gamma 0 such that, of course, these are all positive. The following holds. And the following is for following holds if the x is smaller than gamma 0. So there are some cases that, so in order to make the statement work, for given these two, the other two must be sufficiently small. But when these are fixed, we need to also make sure that the other two are sufficiently small. And when these are fixed, the other one must be sufficiently small. So if you formally write this one in a mathematical sentence in a rigorous way, this is the correct statement. But this is too complicated. It's not like too descriptive and then show you what actually happens. But if you use this notation, then you can just write it this one sentence and it's more descriptive of what happens. So these two and these constants they two are sufficiently smaller than this, and they are sufficiently smaller than this. They are sufficiently smaller than this. So it's more defective. So, lots of cases we also use this notation. But of course, as I mentioned before, there are at least 3 different meanings of this. So one is that the x is big O of y, and the other one is x is small O of y, or this for given y, there exists x0 such that the statement holds if x is smaller than x0. So there are 3 at least different statement. Different way of usage of this. So you have to be a bit careful when you read the papers later, and you need to figure out what it actually means. But at least in this section, let's use in this meaning, so that we don't have. Later we will take several constant, and then this writing in this way without specifying what these functions are. We don't really have to specify this function. So that's quite convenient for us. So we will actually write it this way. Anyway, so back to our statement. We want to prove this hypergraph statement. Statement about hypergraph matching. And it has actually several application. And there are many applications, and one of the applications is about the existence of design. More of an approximate design. So let's define this. Let's say NLK block design is a collection L of sets of size L in this bracket n set. So there are set of n elements. There we consider the collection of L sets. If this satisfies that for any k of set of size k, there is exactly one L set L in here containing K. If this holds, then we say that this is NLK block design. So it seems that I'm over time, so we will resume again in the next lecture. But you might be wondering why, we are suddenly talking about this block design, because right before we were talking about hypergraph matching. And there are some connections. So later when we show that certain block design or approximate version of block design exists, when we prove that, we will use the previous theorem about the hypergraph matching. Yeah, next time we will talk about the relationship between these two, and then we will try to prove this theorem regarding hypergraph matching. I'm not sure whether we can actually finish the proof in next lecture, but we will try and then see how long time does it require.